Meanwhile, mainstream science was embracing particles as points, not strings. For decades, physicists had been exploring the behavior of microscopic particles by smashing them together at high speeds and studying those collisions. In the showers of particles produced, they were discovering that nature is far richer than they thought.
Once a month, there'd be a discovery of a new particle, the rho meson, the omega particle, the B particle. There'd be one particle, there'd be two particles, phi, omega. More letters were used than exist in most alphabets. It was a population explosion of particles.
It was a time when graduate students would run through the halls of a physics building, say, they discovered another particle, and it fit the theories, and it was all so exciting.
And in this zoo of new particles, scientists weren't just discovering building blocks of matter. Leaving string theory in the dust, physicists made a startling and strange prediction: that the forces of nature can also be explained by particles.
Now, this is a really weird idea, but it's kind of like a game of catch in which the players, like me, and me, are particles of matter.
And the ball we're throwing back and forth is a particle of force. It's called a messenger particle.
For example, in the case of magnetism, the electromagnetic force, this ball would be a photon. The more of these messenger particles or photons that are exchanged between us, the stronger the magnetic attraction.
And scientists predicted that it's this exchange of messenger particles that creates what we feel as force.
Experiments confirm these predictions with the discovery of the messenger particles for electromagnetism, the strong force, and the weak force.
And using these newly discovered particles, scientists were closing in on Einstein's dream of unifying the forces. Particle physicists reasoned that if we rewind the cosmic film to the moments just after the Big Bang, some 14 billion years ago, when the universe was trillions of degrees hotter, the messenger particles for electromagnetism and the weak force would have been indistinguishable. Just as cubes of ice melt into water in the hot sun, experiments show that as we rewind to the extremely hot conditions of the Big Bang, the weak and electromagnetic forces meld together and unite into a single force called the electroweak. And physicists believe that if you roll the cosmic film back even further, the electroweak would unite with the strong force in one grand superforce. Although that has yet to be proven, quantum mechanics was able to explain how three of the forces operate on the subatomic level.
And all of a sudden, we had a consistent theory of elementary particle physics, which allows us to describe all of the interactions, weak, strong, and electromagnetic, in the same language. It all made sense, and it's all in the textbooks.
Everything was converging toward a simple picture of the known particles and forces, a picture which eventually became known as the Standard Model. I think I gave it that name.
The inventors of the Standard Model, both the name and the theory, were the toasts of the scientific community, receiving Nobel Prize after Nobel Prize. But behind the fanfare was a glaring omission. Although the Standard Model explained three of the forces that rule the world of the very small, it did not include the most familiar force: gravity. Overshadowed by the standard model, string theory became a backwater of physics.
Most people in our community lost completely interest in string theory. They said, okay, that was a very nice, elegant thing, but had nothing to do with nature.
It's not taken seriously by much of the community, but the early pioneers of string theory are convinced that they can smell reality and continue to pursue the idea.
But the more these diehards delved into string theory, the more problems they found.
Early string theory had a number of problems. One was that it predicted a particle which we know is unphysical. It's what's called a tachyon, a particle that travels faster than light.
There was this discovery that the theory requires 10 dimensions, which is very disturbing, of course, since it's obvious that that's more than there are.
It had the massless particle, which was not seen in experiments.
So these theories didn't seem to make sense.
This seemed crazy to people.
Basically, string theory was not getting off the ground.
People threw up their hands and said, this can't be right.